So in our today's class, we will start with implementation systems and operating system and what is the relationship between them. The relationship is when you write a program in higher level language, the computer don't understand that, as we have discussed in our last class. So what we do, we actually translate the code into the machine code. Now, the each compiler or each higher level language compiler, okay, they can translate their code on their own and they can communicate with the hardware, okay, or what can they do, that they can utilize the operating system, because operating system have already the mechanism, okay, to communicate with the hardware and to do all the tasks the program needs to do. Okay, so the language implementation systems, okay, instead of communicating directly, okay, what they do, they utilize the operating system to do their work rather than develop their own code to interact the hardware directly. Also another advantage for this, or another reason for doing that, because our operating system also can do the file management, okay, they can also make sure the resources are managed properly, they can ensure the security. Okay, so for all of those tasks, okay, the language implementation system like such as compiler, they actually go through the operating system. Now there are three implementation methods we have for our program. First one is the compilation that you are very familiar with. That compiler, you have used compiler starting from C, C++, and so on. But there's another method that you might not have used, that is called pure interpretation. And then there's a hybrid system, that is the combination of compilation and pure interpretation. So before discussing the step, let me tell you what is a compilation is. So whenever you write a program that we call a source code or source program, okay, it looks something like this. I'm taking just one line from the code. Let if A less than B, then we will multiply C with D. So this is just one line out of a code. Let us see that how the compilation takes place whenever you compile the program. So first we have lexical analyzer. Okay, what this does, this actually breaks down your program into small tokens. So you see in this program, if is a token, this bracket is a token, a is a token, then this less than sign is a token, B is a token, and so on. Now the question is, what is a token? Token are the smallest part of a program that the computer or the compiler can actually understand. Okay, so then this is a 4 character, still it's one token. C is a 1 character, still it's a one token. Okay, and so on. There are different types of token, okay, that we'll see in the next chapter. But for now, that's it. Okay, then there's what it does from the source program, it generates the token sequence. Okay, so this is the token sequence. Then there's another program that is called syntax analyzer. Okay, that actually finds out the correlationship between the tokens. Okay, so it makes sense that how to approach the program. For example, in this one, it generates a syntax tree. The tree starts with that like this, that this is a if statement. In the if statement, we have to check for two things. First of all, the assignment of this operation, that is C equals to 1 into D, and we have to do the comparison. So it actually divides the whole program into small tree. And then we have a semantic analyzer, that's a 3 address code that actually generates a code that is similar to the machine code. Okay, that is breaks down into simple instructions that I need to do this. And finally, we use a code optimizer, okay, to optimize the code that you have written or the generated. I will show you an example in the next slide. And finally, we generate the assembly code that looks something like this. So this is our main code and this is our assembly code that was compiled. So this whole process is done into smalls automatically by the compiler. So this is the whole compilation process. Okay, whenever you are doing the compiler course, you will learn what is the lexical analyzer, syntax analyzer in details. But for now, if you just try to remember this example, that what's happening here, we're taking one line of code and then we are dividing the code into small tokens. What is a token? That is a small part of the code that the compiler can understand. Then to make sure the sequence of execution is maintained, we actually generate a syntax tree, and then we have a 3 address code which also further optimized by the code optimizer, and finally we generate the assembly code that looks something like this. So this is our whole compilation process. So this is described here. Okay, so what the compiler does, it translates high level program, that is source language, into a machine code, that is a machine language. Now what it does is it provides slow translation but fast execution, and it has several phases. First is the lexical analysis, converts characters into the source program into small lexical units or tokens. Then we have the syntax analysis, and then you have the semantic analysis. Okay, and finally we have the code generation. So the description is given here, you can have a look. Now, as I said, there is a step here that is called the code optimizer. So what it does, let me show you here. So if you look at this code, okay, the first code and the second code both are same, but you can see that the first code is not optimized, okay, but the second code is. Okay, so what the compiler does, okay, it actually sometimes optimize your code. It actually removes the redundant lines from your code. So first look at, if you look at this example, what we have done, we have declared a variable that is integer a. Then in the function integer foo, we have assigned a equals to 1, and then if a greater than 0, okay, we have assigned a equals to 3, else we have returned a equals to -1. Okay, and then we have returned a. So what happens if you look closely, okay, if I assign a equals to 0, obviously this execution will this one will be executed, right? So this part of the code will be executed as I am assigning a equals to 0, so only this part of the code will be executed. Okay, so this will never be executed. So there is no point actually of keeping this line or doing this if statement. Okay, so the compiler, okay, have the ability to understand it, that as I am assigning a equals to 1, always this line will be executed. So there's no need of if statement, there is no need for this else statement. So what the compiler will do, remove all these unnecessary lines, okay, and then he will actually make it like this. So foo, again the same function, okay, a equals to directly assigned with 3, and then a will be returned. So this is an optimized code. So what, there's another term here that is called race condition problem. I'll come to that later, but this is the basic idea of optimization. Okay, now let's go back here. Now the compiler, what it does, it improves the program, okay, usually in the intermediate code version. Okay, so we're talking about here where we generate the 3 address code and optimize it. So what it does, when you say optimization, it makes the code smaller, faster, or both. So in our case, this code is obviously smaller. It is also faster, okay, because you don't have to waste time executing this line or using the comparison of if statement. And it's the optional part of a compilation, okay, because even if you don't compile do the optimization, it will not change or it will not have that much effect in terms of execution. Okay, yes, the speed will differ. Okay, it will previously it will have, now it will have more it will execute faster, but apart from that there's no changes in terms of functionality. Now, some compilers are incapable of doing any significant optimization. So this is actually not done by all the compilers. Okay, so it omit some part of the code in your program. It changes the execution order of the code in your program. So this is all about the optimization that you have to remember. Okay. Then there is the symbol table. So what the symbol table does, it actually serves as a database for the compilation process. So what the database does, let's assume that you have written this if statement. So as a programmer who have learned C programming, you know that whenever I want to compare something, I have to write this if statement. Okay, so you already know that is stored in your database, okay, in your memory. Okay, so compiler, okay, they also have to know this, that if someone writes if, I need to do this operation. If someone writes equal, okay, I need to assign the value to here. So for that, okay, we use this symbol table. This symbol table holds all the primary contents, okay, of a language. So what is the meaning of integer main, what is the meaning of return 0? Okay, so every tokens or small part of the program that you can write, okay, all of them have their meaning in the symbol table. So whenever in the compilation process, if you look closely, first you give the source program, okay, the source program goes to the lexical analyzer. Okay, so this the intermediate steps, that means the steps that we see here, okay, they're all we have talked about in the last picture. That means from, I'm talking about this one. Okay, so these steps. So where the symbol table is, it actually works parallelly with all of these steps. Okay, so what happens first, the program starts, again goes to the lexical analyzer, and as soon as the program goes to the lexical analyzer, okay, the symbol table is then generated. Okay, it checks what all the symbols are, it finds the meaning of the symbols, okay, and then it stores them into the symbol table. Then when the program, the lexical unit goes to the syntax analyzer, again it checks for here that, okay, I have this symbol, do you know the meaning of this symbol? If yes, it returns the meaning. Okay, if not, okay, it finds the meaning. And then we have the intermediate code generator, and this is where the actually symbol tables really comes in handy. Okay, so from the parse tree and the combination of intermediate code generator and the semantic analyzer, we'll don't worry about the semantic, we'll again discuss it in the next chapter, but right now if I discuss all the components, it will be very confusing for you. So what they communicate between each other, okay, to find the meaning of the symbol. If there's any missing symbol, they also let it know. Okay, and finally we optimize the code and we generate the intermediate code, and this is optional again. And after that we generate the final machine language code, and the compiler takes input from the user and the code starts running. So all the steps, okay, these are mandatory steps. The symbol optimization is optional step, and then we have to use the symbol table to keep track of the each words, because if we don't keep it here, what will happen, every time you face a new token, the compiler has to go back and search from their own primary dictionary. So you can think like this, that suppose you are trying to speak a new language. Okay, now whenever you're trying to speak a new language, you have written a program in the new language. So what you can do, okay, you can, whenever you face a new word, you can go back and look into the dictionary, okay, where all the words are stored. Or what you can do, okay, so you can first search, okay, so this is my program, and in this program I have this 5 word. Okay, so you need to find the meaning of these 5 words, okay, and store them into the symbol table. So anytime you forget about any of these 5 words mean in the in any of the steps, you can just go back and look here, okay, in this symbol table. You don't have to go back and look to search in the dictionary. So I hope you understand the difference here. Okay, in this one I'm making a small dictionary of all the words that I find in the lexical analyzer. So in this way, I don't have to go back and search the whole library for the meaning of this tokens or the words. So this is the process of compilation. So what is the question here? The question is that first you know that this is what is the compilation, what are the 3 implementation methods. Then you will know what is the how the compiler works. Okay, you don't have to memorize per se this diagram or something. You don't have to draw diagrams in the exam. Okay, but you just have to know that these are the steps. So lexical analyzer, syntax analyzer, semantic analyzer, code optimizer, and code generation. You have to know one line of description of for each of this step. Okay, now these ones are easy to remember, like code optimizer, code optimizer, code generation, syntax analyzer, lexical analysis. You just have to remember the semantic analyzer a bit, and then how the optimization is being done and what is the role of symbol table. And again, you don't have to memorize this diagram as well. Okay, now apart from all these that we have seen, there are some additional technology terminologies that we have to use. For example, load module, okay, linking and loading, libraries. Okay, so I think all of you are have heard about this. So let me start with the simple one that you have heard most, libraries. Okay, so in addition to the system functions that we provide in a program, sometimes user, okay, they must have whenever compiling a program, okay, you can actually add new programs, okay, new functions, okay, in the your current program. Okay, that means let's think about a simple example that you have written your own search function. Okay, so what you can do, okay, instead of using the system search function, okay, what you can actually create your own search function. You can link to that search function that you have compiled before. Okay, and those are called libraries. Okay, so the users write a program, and then they actually keep the program as a collection. So what you can do, if you want to use that collection, you can use it as a library. So that's it. Okay, Then the linking and the loading. So whenever you actually run a program, sometimes what happens, the compiler has to fetch different part of the code from different user programs. Okay, and it has to fetch the resources. So all these are actually done by a system program that we called linker. Okay, and finally the load module, that the user program and the system work together. Okay, so whenever you take input, you actually get an output. All these are actually the tasks of the executable image load module. Whenever you actually compile a program, you will see that there is an executable file that are created. Okay, so for example, I have written a very simple C program, then I have compiled the program. So first time when I run the program, okay, I will see that if you go back to the folder where your program is stored, you will see there are three different files are created. One is your .c file, okay, and then you'll see there is a .exe file. So that's where our executable image is. So if you directly click there, okay, the program will start executing. And now, one more point, the linker that we are talking about here, okay, it not only links between a given program, okay, it also links with other functions as well. So it links with system functions, it links with user functions. So that is the task of the linker. So this is a simple process that explains of a normal function. So this is the main program that calls the printf function. Okay, so whenever it goes through the compilation process, the printf function, that means the add of printf, it is stored somewhere into your computer or in your system. So in the loading phase, what it will do, okay, it will go to the, it will find the detailed version of the instruction. So the printf instruction will be then transmitted to add of printf. That means add printf here, or add printf instructions here. So this line means this one. Okay, so add printf instruction here, or load printf instruction here, no matter how you want to put it. Okay, and after that, what the in the loading phase and the linking phase, what it will do, this instruction is stored somewhere into your computer. So this instruction will be, let's assume that this is the address space of printf. That means the details of the printf instruction, that when how to print a variable, is stored into this memory address. So what it will do in the linking phase and the loading phase, it will actually load the address. That means if I want to execute this line of code, I have to execute the instruction that is stored into this address. Think like this, that this is a printf function, and I'm asking you that make sure where it is. So you have found it, okay, this is in this address, the instruction is in this address. So I will just copy the instruction from this address, and then I will store it into my main program. So whenever you are writing a compiling a program, all the programs actually happens like this. The instructions are stored somewhere into the computer. Okay, so in the linking phase, okay, all the addresses of those corresponding instructions are actually binded with the line. Now, finally, to do this, okay, we again have to come back to the von Neumann computer. So we have talked about what is a von Neumann architecture, okay, and how it works. The simple idea is that it follows the operating system simple cycle, fetch and execute. So if you have a 10 instructions, okay, it will fetch the 10 instructions and it will execute the 10 instructions. That's it. Okay, there's nothing new here. And it also takes the help of a program counter, which counts that, okay, so now I need to execute line number 34. Now I need to execute instruction number 35. Then I need to execute instruction number 36. So it keeps the count. Okay. Now, what is the problem with this? So there are some examples given here just for your understanding. You can have a look. So as I was saying, that there's a problem in the von Neumann architecture. Okay, what is the problem? We call it the bottleneck problem. Okay, so normally the idea of bottleneck is very simple. There is a, let me give an example related to traffic jam. So let's assume this is a road. Okay, so this is a road and many cars are coming from this, and suddenly there is a bridge here. Okay, so the bridge goes something like this. So all, so what happens, that cars that are coming from this direction, let's say there is one car coming from this direction, another from this direction, another car from this direction. So there are four cars, let's say, coming from this direction. Even though there four cars can parallelly go in this line, okay, in this part of the road, okay, it has to wait because not all the cars pass at the same time. So this is called bottleneck. Okay, so you see this is almost shape of the bottleneck. Okay, that's why I call it's called a bottleneck problem. So in the von Neumann architecture, we also face this bottleneck problem. The question is why? Because the CPU, the processor, actually can execute a very multiple instructions, okay, millions of instructions at the same time. Okay, the speed of the processor is actually very high. So whenever they're selling you a computer, they actually sell you in terms of processor speed. Okay, so whenever you go to buy a computer, they will say, my that said, this computer is very fast. Okay, you should buy this one and that one. But as an engineer, if you don't understand the bottleneck of your system, you will never get the best out of it. So let's say you're buying a new computer, okay, and they have said that, okay, do you want to buy i7 or i3? You're thinking, okay, I should buy i7 because i7 is faster. Okay, it has a high number of instruction that it can execute. Okay, so you're happy, but then to make sure the budget, okay, to fit in the budget, you have bought a RAM of 4 GB, okay, and some related configs. Now what will happen, even though your system is i7, the processor, okay, it will never be able to work at its fullest. Okay, because the rest of the system, they have the limiting capacity. So whenever they're selling a computer, they will not tell you this. Okay, they will not explain you how the bottleneck work. They just want to sell the product. You have to understand it as well, that if I have a 4 GB RAM, okay, there is a very small benefit I will get from an i7 processor. Okay, because I need to make sure the rest of the system can work on the same speed as well. Okay, so how do you understand it? We have the motherboard for that. Okay, you have to have the RAM for that. Okay, and so on. Okay, so this is the idea of von Neumann bottleneck, that normally in the von Neumann bottleneck, we have seen that there are three, it is divided into three parts. Okay, it has a memory where the instructions are stored, and from those instructions, what we do, we execute, fetch those instructions from our memory and then execute. So if the memory cannot fetch, okay, with the same speed as the CPU, in that case the CPU has to wait, just like the example that I have given in the road. Think about the road, about the CPU, but the bottleneck, okay, is the memory. So that's the problem with the von Neumann bottleneck. So if you want to make sure that you get the best out of your computer, okay, you have to understand these limiting factors that you have in your computers. So if you can manage the higher RAMs, okay, and related bus and so on, in that case you will get the best out of your computer. Now the second interpretation method, implementation method, is, the first one was, as you have seen, compiler. Then we'll talk about the pure interpretation. So before going to the interpretation, let me show you the difference between these two. It will be easier to understand. So the compiler, what it does, it takes the source code, okay, then it does all the steps that we have seen before. Okay, these are steps. Where is it? Hmm, yeah, lexical analyzer, syntax analyzer, semantic, code optimizer, code generation. And after doing all this, uh, what it does, it generates an object code which combines the data and the result. So this is the overall step of the compiler. Interpreter, what it does, okay, it actually takes the source code and it also takes the data, okay, and then it generates the result. So the first difference is here. I will go to the definition now, but before the look at here, first the compiler translates the source code, then it combines the data and then generate the result. The interpreter takes the source code and the data at the same time, and then it generates the results. What is the advantage of compiler? Compiler provide you with first program execution. It also exploit the architecture feature that you have in your computer. What is the advantage of interpreter? It is easy to debug, flexible to modify, and machine independent. Now, what are the disadvantage of compiler? The pre-processing of a program, you have to understand all the errors there is, and it has also have high complexity. But in the interpreter, you have the execution overhead and the space overhead. Now, I will try to explain all these points one by one. But before that, let me go back here. Sorry, here. So what is the primary difference between compiler and interpreter? So if I have to say in one line, I will say that in the compiler, the whole source code is compiled at once. And whenever you use the compiler, it will show you all the errors at the same time. So like if you run a program and if you have 5 errors in the compiler will first process the whole program, and then it will tell you that, okay, I have tried to translate the whole program, but I have faced these 5 errors.